Okay, so the standard model, first learning outcome is about orders of magnitude. So first of all, do you know what we mean by an order of magnitude? Simple description there would be the power of 10. Right? So if you described any number in scientific form with powers of 10, then the number, the 10 is raised to as the order of magnitude. But what the learning outcome says is give examples of a range of orders of magnitude. And how that's tended to be tested is maybe to ask you to slot something in position. Okay, so for example, you might have to sort things into order. So kind of key ones. Right, size of an electron stroke or quark. And they're kind of 10 to the minus 18. Size of a proton. An atomic nucleus. Now that's maybe a key one, that you're aware of the kind of size of a nucleus compared to the size of an atom. Right? So atoms are around about 10 to the minus 10. Not that I would expect you to memorize that value precisely, but you should be aware that an atom is about 10,000 times, right, further across than a nucleus. Right? The difference in scale there is huge. And then kind of when we go to the other extremes, right, so there's lots of examples given in your notes, but when we go to the other extremes, knowing that a moon, right, is a step up, and then a planet would be even bigger, and then a star even bigger, and so on, galaxy, right, kind of getting to large sizes, right, so in the larger orders of magnitude. But the only one I've ever seen kind of mentioned numerically is that size of the atom versus size of a nucleus. Okay, so that's probably the kind of key words in terms of examples. Okay, learning outcome 2 is the standard model. Now, once again, I don't think you'll get a question which simply says, draw the standard model, right? But being able to recognize, so for instance, naming some quarks. Okay, so recognizing the standard model consists of the quarks, and the way it's organized as well, so you've got generations. So starting with quarks, you've got up, down, charm, strange, top, and bottom. Okay, and that's kind of first, second, third generation. Then going with that, you have the leptons. So you've got the electron, and what's commonly just called the neutrino, but its full name is actually the electron neutrino. And then you've got the muon and the tau particle, and each of them has a neutrino to go with it as well. So the muon neutrino, and tau neutrino. Okay, so recognizing that sort of structure. And then the last part of the standard model, right, is the force carriers. Okay, which consists of the photon, gluon, and the Z and W bosons. Now there is actually Z plus and minus. And then kind of sitting beside all this, but giving everything its mass, the Higgs boson. Number 3 is about the evidence for subatomic particles. Right? So the kind of first piece of evidence we came across was in beta decay, that we couldn't actually explain beta decay properly, right, without there being another particle. So it looked like conservation of momentum was being broken unless there was somehow another particle there. But even going back, the first proof right, the first proof was Thomson's discovery of the electron. So remember, we talked a wee bit about Thomson looked at how these what were called cathode rays, which we now know are electrons, bent in an electric field. And he found that from that you can get information about their mass. And he found that they were lighter, significantly lighter than the lightest element that was known about, hydrogen. So the only explanation could be that there was something smaller than the lightest element, i.e. something smaller than atoms. So Thomson's discovery of the electron is the first thing. I mentioned briefly there beta decay and the idea of conservation of momentum. In beta decay, it could only be explained by the neutrino. And the other one is called deep inelastic scattering, which is basically what they're now doing at CERN. It was done before that at different places. And it's very similar to Rutherford's, how we got Rutherford's model of the atom, right? By firing alpha particles at gold foil and looking how they deflect. Except with deep inelastic scattering, what you're doing is firing protons at each other and seeing how they deflect. And from that you can work out what the structure within the protons actually is. And it suggests that there's kind of 3 bits to that structure. So that's how we know protons consist of 3 quarks. Okay, 4 is about antimatter. Every particle in the Standard Model has an identical partner in fact, I'm going to phrase that slightly differently. Right, it has a partner identical in every way apart from having the opposite charge. And that even includes the neutron, because although the neutron is overall neutral, it is made up inside of charged particles. So the anti-neutron has those same particles, but they're antimatter equivalent. So these are called antimatter. So when matter and equivalent antimatter meet, so for instance, a proton and an antiproton, right, a neutron and an antineutron. So when these meet, annihilation takes place. Leaving 2 photons of pure energy. So the matter disappears, and what you end up with is 2 photons of pure energy. So these can be detected, first of all, as evidence for the existence of antimatter. But talking about an actual use, these can be detected in PET scans, which stands for positron emission tomography. Right? Tomography means scanning. So you're basically introducing positrons, which remember is the one antimatter particle which has its own name, is the anti-electron. Right? So they can be detected in PET scans, right, and used to image, right, soft tissue. So number 5, we've already included leptons in our standard model because leptons, which stands for light ones, are what we consider to be fundamental just now, i.e. we don't see any structure within them. We don't think they're made up of anything else. Hadrons, which stands for heavy ones, then they are the particles which are made up, right, of other things, right, made up of quarks basically. So hadrons are particles made up from quarks. And there are 2 types of hadrons. So you get a lot of new language here you've got to learn definitions for. Right? Baryons are made up of 3 quarks. And the 2 examples I would expect you to know, protons, right, which are up, up, down quarks, and neutrons, which are up, down, down. Mesons are made up of 1 quark and 1 antiquark. Now, I don't think there are any examples there that you need to. Okay, number 6 is about the 4 fundamental forces. So first of all, you need to be able to name them. Right, but we'll also need to know a wee bit about them. Right, so electromagnetic, weak, nuclear, and strong nuclear. Often they are just called the weak and strong force, but their full name is weak nuclear, strong nuclear, and gravitational. Okay. We need to know a wee bit about each of these. So for instance, you should know that the weak and strong nuclear force are both very short range. Right? So basically they only act within a nucleus. Right? So weak and strong, very short range, only within a nucleus. It's a strong force that keeps a nucleus together. It's a weak force that causes beta radiation, right? Causes one of the neutrons to change into a proton and electron pair. So electromagnetic and gravitational forces are long range. Basically infinite. Now we've seen in gravitation already that they follow an inverse square law. So as you double distance away, they will quarter in size. Could be asked really is about putting them in terms of strength. Okay, so not surprisingly, the strong nuclear force is the strongest, followed by the weak nuclear force, followed by electromagnetic, followed by gravitational. Now this is really from the perspective of kind of atomic and subatomic particles. Obviously gravitational is kind of the most significant for you or I, or in terms of what we experience in every day. And it probably feels like the strongest force. But without these other forces or nuclei that make up our bodies wouldn't stay together. Without the electromagnetic force, right, then the atoms wouldn't stay together, atoms wouldn't bond to form molecules, and so on. So although gravitational is the one that we're probably most conscious of, right, it's actually still the weakest of all the forces. Right, for the strong nuclear force, it's gluons. For the electromagnetic force, it's photons. For the weak nuclear force, it's W, Z minus, and Z plus bosons. And then lastly, for gravitational, and it's only recently been kind of good evidence for its existence, so that's why it's not yet fully accepted into the standard model. The last bit I'll just add as a wee discussion is this idea of exchange particles, how they can be used to explain a force. And the best example we could kind of give you is if you had two people on ice, if they were throwing a heavy mass between themselves, when the first person threw it, they would move backwards. Okay, I'm going to do some fantastic drawing here. Right. When they throw, say, something like a medicine ball, then by Newton's third law, they would move back that way if they're standing on ice. When the other person catches that ball, then they will get pushed that way. So the ball is the concept of these force exchange particles. Right? That the two objects here, the two people, can exchange a particle, and that is what results in a force. It's a way of explaining a force. This one is about beta decay. Right, so do I think you need to memorize this diagram? I don't think so, but it does seem to come up quite a lot, so I'm not 100% sure. But basically beta decay consists, remember, of a neutron. And if we describe the neutron, remember, as a down, up, down, then within an atom, which is unstable, right, within a nucleus which is unstable, then the down particle can change into an up. That up continues as an up, that down continues as a down, but that then leaves you a proton. And it does that involving a W particle, which in turn splits to produce an electron and an antineutrino. Now, the symbol for an antineutrino is a Greek letter mu with a bar above it because it's an antineutrino. So that's kind of what's happening within standard beta decay, which is known as beta minus decay. You can get beta plus decay where a positron is produced and a neutrino. Right, so beta minus gives you an electron and an antineutrino, beta plus a positron and a neutrino. And I've already mentioned it in the context of evidence for the existence of antimatter, but also it's taken as evidence for the existence of neutrinos.